I'm going to talk about work, and work in the physics sense is equivalent to the change of energy of a system. So external work on a system is equal to the change in energy. And strictly speaking, work is equal to the change in kinetic energy, but we play a little game like I talked about with potential energy. And potential energy is just work from either a spring or the Earth's gravitational field. So in that case, we call the system the object and the Earth, or the object and the spring. Okay, we'll talk about that a little bit. Let's just talk in really basic terms about what causes this change in energy, what transfers energy into or out of a system. And to do that, I want to look at just I'm pushing an object, and I'm pushing on it. It has mass m, and I'm pushing with the force F. And there's a little bit of friction, force of friction, going in the other direction. Okay, so this will be my applied force, and there's force of friction in the other direction. So I'm moving it in this direction. I'm pushing it in this direction. Now, if there was no friction, then clearly me applying a force, F equals ma, there would be an acceleration, there would be an increase in kinetic energy. So this force would be doing work and is doing work, okay? Think if I didn't have that force there, if I'd given it a shove earlier, it's sliding this way, and the force of friction is that way. So the force of friction would be doing negative work. It would be removing energy. The kinetic energy would be decreasing, okay? If we took both of those away, and we just had a mass sitting on a flat surface, well, no work is being done really because there's no change in kinetic energy. If we took away the ground, then yeah, that would be doing work. Gravity would be doing work. So let's take a look at that free body diagram and think of what we just talked about. Here's the force of gravity. I'll call it mg. Here's the applied force. I'm going to assume I'm pushing harder than friction, but that really doesn't need to be the case. And then we've got a normal force. There are no other up and down forces. Therefore, those two are equal. And what I want to do now is I want to look at what kind of work these things are doing. We said this was adding energy to the system. This was taking energy out of the system. Friction was taking energy out of the system as it moved some displacement delta x. So it turns out that an object moving in a certain direction, the work or the change in energy, how much energy is being put into the system, is going to be equal to this times this, the force times that. But remember, there was a weird thing where that was negative. Is there something magical? Well, it turns out if they're in opposite directions, you're taking energy out. Friction's a great example. Another example is this. If a car is rolling towards me, it's going in this direction, and I push to stop it. While it's moving this way, I'm taking energy out of the system. So if they're in opposite directions, work equals F times delta X, positive if they're in the same direction, negative if they're in opposite directions. But there's another thing that's going on. Normal force isn't really doing any work. Okay, so it turns out that there's an operator that takes care of all those cases. Cosine of theta. And I like to actually say cosine of between, because there are going to be a whole lot of angles going along. You don't always just plug in the only thing you see with degrees. This is the angle between the force vector and the delta x vector. Okay, so let's take a look at these. And let's start putting some numbers on here. Here's, let's say a 20 kilogram box, or 20 kilogram box. So there's 200 newtons there. If it's at rest in equilibrium vertically, 200 newtons there. I'm going to say I'm pushing with 100 newtons, and the force of friction is 20 newtons. Okay? So each of these things, we can figure out how much work is done by each of them. And I'm going to rewrite my equation so it's not blocking my view. So if we have F delta x cosine theta, for every one of these elements, we can figure out how much work it does. And to do that, we have to be really, really careful about that angle. Okay, so let me write this. Work. W is the symbol. By the way, it's measured in joules because it puts energy in and takes energy out. It's got to have the same units. Work is, yes, it's equal to the change in total energy of the system, or change in mechanical energy of the system, but it's also equal to F delta x cosine of the angle in between. And I'm going to write these as vectors. Work isn't a vector. It doesn't have a direction. But these things do, and those are important for figuring out what that angle is. And again, I'm going to write between. If you have to use your fingers, use your fingers. Okay, let's figure out all of the work done by each of these things. First of all, the work done by me. We need to know what the delta x is. I moved it 5 meters. Okay? I moved it 5 meters. I'm just saying that. Moved it 5 meters. So the work done by me is my force, 100 newtons, times the displacement, times the cosine of the angle in between. There's the 100. Point in the direction of the force. Point in the direction of delta x. That angle is 0. Cosine of 0 is 1. So I did 500 joules of work. Whether there was friction or not, me pushing in that direction for 5 meters with a force of 100 newtons gives 500 joules. If there was no friction, I would have increased the kinetic energy by that much. Okay? Let's do the work done by friction. Work done by friction is 20 times 5, right? Force times delta x times the cosine of, I'm using my fingers, cosine of the angle between 20, 5. That angle is 180. And that cosine is -1. So this is -100 joules. If those are the only two agents of work on this object, it will gain 400 joules of kinetic energy. But let's keep going because there are 2 more forces. Work done by the normal force is going to be 200 times 5 times the cosine of the angle between the force and the delta x. That's 90 degrees. Cosine of 90 is 0. Okay, so if they're in the same direction, opposite direction, perpendicular, those are very easy. Same direction, it's just +1. Opposite direction, -1. Perpendicular, 0. No work is done by the, I did newtons, I want joules. No work is done by the normal force. I'm doing a little extra work here because I wrote the wrong unit. There we go. Work done by gravity, 200 times 5. Force, delta x, 90 degrees. 0 is the cosine of 90, 0 joules. So the total work, 400 joules. Okay? Now, what's important is I really always want you to start with this, change in total energy. And in this case, remember I said potential energy is really just what we use to incorporate the work done by gravity, so we don't have to do that every time. If you represent all of these, this is the change in kinetic energy. But if you represent gravity with potential energy, then it's one of these. I'll show you what I mean by that. Okay? So work, force, delta x, cosine of the angle in between. And of course, these don't have to be 0, 90, and 180. They can be any angle. And I'll come to that in a minute. After I take half hour erasing everything. Okay, so let's look at a block being, that same box being pushed at an angle. Okay, it's a grocery cart. Okay, and this time I've got a grocery cart on a flat surface, 10 kilograms I push with 100 newtons at an angle of 30 degrees from horizontal. Okay. There is 20 newtons of friction again. So we do our free body diagram. I've got 100 is mg. I've got the normal force. I got to wait a second, right? So my free body diagram looks like this. mg is 100. I'm pushing with 100. Friction is 20. Normal force is up here. It's actually going to be quite big. So I do my free body diagram. Then I pick a frame of reference. Don't really need this time. But, okay, this is mg is 100. Sorry that it's slanted. Friction is 20 newtons. This breaks down into 100 sine of 30, which is 50 newtons, and 100 cosine, which is 86.6 newtons. And here's the normal force, would end up being 150. I'm going to show you why you don't even need to do that step. The only reason you would need, when you're talking about work, the only reason you need to do that step is if you need to figure out the normal force or if you're trying to find acceleration. But we can do this. You can either break it down and do all the work done by these things with these components, or you can just use this. Okay, and let's say I move it 10 meters, too many tens, well, 10 meters. I move it 10 meters that way. In this case, once again, the work done by the normal force, F delta x cosine of the angle in between, it's 0 because they're perpendicular. Force perpendicular to the motion does no work. Okay, so no work done by the normal force. I didn't even need to break things down. I didn't need to find the normal force to figure out what the work was. Work done by gravity, 0. Work done by me, yeah, I could break it down. And I could say this does no work, this does work, but I want to concentrate on this, that 100 at an angle of 30 degrees. Okay? 100 is the force times delta x, 10, times the cosine of 30 degrees. And that ends up, okay, remember force, delta x, cosine of the angle in between, that angle is 30. And so we have 1,000 times 0.866, so we have 866 joules of work done by me. Friction, 20 times 10 times the angle in between, cosine of the angle in between, 20 times 10, cosine of 180, which is -1, and that ends up being 200 joules. Okay? So really, since these don't do no work, 866 minus 200, 666, the devil's energy. That's the net work. That's going to be equal to the change in the mechanical energy of the system. Okay? The very last thing I want to do is I want to point out that yes, we can figure out the work done by gravity, but things moving relative to gravity happen so often that we generally don't do it unless it's explicitly asked for. What we do is we very frequently, we're talking about conservation of energy and things like that, we don't really worry about the work done by gravity as such. We represent it as the potential energy. Okay, let me show you what I mean. Ball goes down a ramp, okay? And right here, it's 4 meters high. And here's the block, frictionless, okay? So, starts from rest, comes down to the end. Now, ordinarily, we solve this like conservation of energy because we consider the block and the earth to be part of a system. So we say E total equals E total prime. If it starts from rest, we'll say MGH, or potential plus kinetic, equals potential plus kinetic prime. And up at the top, mg times 4 let's just do mgh plus kinetic energy, I'll just say it's zero velocity, equals at the bottom, if we call this 0, 0 plus 1/2 mv prime squared. Now, let me show you. The way we were just talking about when we calculate the work done by gravity, that if we do the work for every possible force, that shows the change in kinetic energy, right? But if we include potential energy as part of this, we can just do this as conservation of energy. Let's pretend we didn't. The work done by gravity would be mg times this delta x times the cosine of that angle. It ends up being the sine of that angle. And that ends up just being mg times h. So this is the work done by gravity. Okay? If gravity does that much work, then we could say Wg plus the kinetic energy at the beginning, which was 0, equals the final kinetic energy. So that's what I mean by when we do potential energy, gravitational potential energy, we're ignoring the work done by gravity. It's included in this whole thing. Okay? So you very rarely do have to calculate it. That's a little more of an AP thing that gets done. So the final summary on this whole thing is that work is a way of transferring energy from one system to another. And that's the very first thing we learned about work, and that's the biggest thing I want you to remember about work. Work equals change in total energy of a system. And for our class, unless I say calculate the work done by gravity, we are really talking about this as the mechanical energy, so the potential energy plus the kinetic energy, how much it's changed, the delta of this. But we have a way of calculating it for each individual force, which is F delta x cosine of the angle, very importantly, between. Notice that every time we did work, I used my fingers and I figured out the angle between those things. In that last example, I didn't use 30 degrees for every single theta, right? It was always the angle between those two vectors. And if you do that very carefully, you'll be in great shape. What we can do now is, I could have a system, and I could say, here's a force, I move that system. The system could be a shopping cart. And I can figure out how much will the energy of that system change. So now we've completed the entire unit. We're going to do one more thing, which is we're going to look at the rate of doing work. Okay? If I push that shopping cart slowly or quickly, it's a very, very different result. And so the energy I add, how quickly do I add energy to the system? And that's called power. We'll look at that next.